Hi, so this is our project. We wanted to do something around pathfinding, so we looked into flow fields and crowd simulations. Now, my part in particular is about generating these flow fields, so we can use them for pathfinding. You might be wondering what a flow field is. Well, in traditional AI pathfinding, you have a character, let's say, generate a path towards their goal using some pathfinding algorithm. And you would do this for every single character in the game. Now, this is fine for most cases, but if you're trying to, say, simulate, well, thousands to hundred thousands of characters, it can become quite performance intensive. So what people do is they actually generate flow fields. And what it basically is you're kind of pre-computing the pathfinding and then putting that on the terrain, right? So you see here, these arrows are moving forward, and you see you hit a wall, and then you go around the wall. You see these arrows around the wall, and then it goes towards the goal. Now, this actually is quite efficient. So because the character only needs to check the terrain, and they just know the direction, but it actually becomes a problem if you're trying to change the terrain, because when you change the terrain, say for example if you remove this wall, then the arrows are become irrelevant. You could just go straight now, so you actually have to regenerate this flow field, and that itself can be quite expensive to do. If your game is static, then it's fine. You don't actually have to regenerate. You could just, if in fact you can actually do one better, you could bake the entire flow field into, say, a texture or something, kind of like how you bake lighting, and then before you even run the game, you have your flow field ready. You don't have to generate anything. But if your game is dynamic, then you hope that you're generating a flow field quick enough, and that's what I've tried to do. I've tried to make it so that this flow field in particular is optimized and very fast. It's actually quite a development challenge. So for this particular map, I could actually generate this flow field in under a second. But it actually depends on the amount of cells over here, because the more cells there are, the more computation it needs to do. So it definitely depends on the size. So it definitely, when it gets bigger, it becomes a little more slower. But hopefully it's fast enough. Obviously, if you put this in an actual game, hopefully you could have it have the flow field processing in the background, and then once it's ready, you could actually put it into the game, so you wouldn't have to wait. You would have it happen asynchronously. So let me show you how I made it and how I developed it. Right. So I started with making the grids and the flow fields. So the grid that I made is actually quite flexible, whereas you can have any size and any number of cells in between inside it, so you can adjust that, and you could adjust it based on how big your character is. Now, when I started making the grid, I kind of thought it would be faster if, instead of for each path for each cell, when you're trying to figure out the best way to go to goal, you actually have to check the obstacles, right? Where are the obstacles? If there's a wall and whatnot. So I kind of just I just kind of stored I kind of do one pass, stored the obstacles into each cell, and each cell can know whether it's been blocked by an obstacle, a wall, or something like that. So if it's blocked by a wall, it knows to go around it and stuff like that. So yeah, so I started with that and tried to make it more efficient. So as you can see here, we can detect the walls, and it's quite a lot of cells here. It's quite insane. Now, as much of it as it's a performance problem, it also is a very big memory problem, because you don't want to be using 4 gigs of RAM for your game for just for the flow field. I had to basically efficient on memory, make efficient data structures for that memory as well, for storing all these. Once I've done that, I could move on to making the flow fields actually work. So the way it works is not too complicated. For each cell of this thing, you run a pathfinding algorithm towards the goal. So as you can see here, so for example, if you take this cell, do a star for a star algorithm, or like any pathfinding algorithm, you could do Dijkstra as well. But for my scenario, I could use an a star algorithm that I optimized, and you could run this towards the goal, and once you know how the best way to go to the goal, you could point in that direction over there. Now, you actually need to run this algorithm. You can't just point towards the goal, because if you just point towards the goal and say, what happens if there is a wall here? Well, then it actually has to go around, right? Then the path, the flow field path, is not that way, it's that way. Because if there's a wall here, then if you just assume that the best way to go is that way, then it would go here and then it would go there. It wouldn't be very efficient. So you would need to run this algorithm to figure out the best direction to go, the best course of action, I guess. Now, once you've done the pathfinding algorithm, it's just a matter of doing it for every cell, and you have this kind of like flow field to start with. And I guess some more optimizations here and there, and we have a lot of cells that you can generate. And yeah, it's quite amazing. So one big optimization I made was multi-threading. So the region actually generates in a different thread, and then you could do that. I also kind of made use of heaps in the A-star algorithm to make sure that it's fast. And yeah, that's basically that. I kind of wish that I had more time to, if I had more time, I would have been able to split the grids into multiple parts, because if you have like a really big game, for example, you wouldn't want the entire flow field to take over the entire world, because that would just cost a lot of memory. So what you do is, if you can split it into parts, you only put the grids in specific locations where you can navigate across. That way you can save a lot of memory space, and you can also save computation time as well. So yeah, I hope you guys found this project interesting, and thanks for watching.